All right, so now we're going to take a look at a couple of calculations to show how we calculate the energy of photons, as well as the binding energy of electrons from a metal, for example. Okay, so the first question here says calculate the energy in joules, oops, of a photon with a wavelength of 5.00 times 10 to the 4 nanometers infrared region, and a photon with a wavelength of 52 nanometers, which is in the ultraviolet region. And then part C, calculate the maximum kinetic energy of an ejected electron by the photon in part B from a metal with a binding energy of 3.7 eV. EV here stands for electron volt, which is another unit of energy, and we'll talk about this in a little bit. So what we'll do, we'll focus in here on part B in this question, because part C relates to part B more than it does to part A. All right, so we're told here, let's look at part B. We're given a photon. So again, one single packet of light energy. And the wavelength of that is 52 nanometers. So right away, we're given a wavelength, 52 nanometers. And what we need to calculate is the energy in joules. So the only relationship that we know that relates energy to wavelength is the E equals h nu. Right, so we have energy here. We have Planck's constant, which is always going to be provided. And then nu is our frequency. But we are given wavelength. So is there a relationship between wavelength and frequency that we know, right? And the answer is yes. We can use C equals lambda times frequency, right? We saw that in the earlier sections. And what we can do is rearrange this equation, solve it for nu, so that then we can substitute nu back into our equation. So if we rearrange it, we end up with nu being equal to the speed of light c divided by our wavelength, which is lambda. We can take this now and we can substitute it into our equation that we have. So E then is equal to h times c over lambda. Okay, so we have h, which is our Planck's constant, right? And Planck's constant, 6.63 times 10 to the negative 34. We substitute those values in. 6.63 times 10 to the negative 34. And I keep track of the units as well. Joules times seconds. Okay, that's H. And then that's going to be times by the speed of light. So 3.00 times 10 to the 8. And that's meters per second. Okay, so meters times second to the -1, same as meters per second. That's now divided by the wavelength. Our wavelength is 52 nanometers. So you will notice, hopefully, that there's a problem here. And that is that we have nanometers down in the denominator. The only other place where we see distance or length is in the numerator, and that's in meters. So what we would need to do is we need to convert this nanometers to meters, and we can actually set up that conversion right down here. Okay, so our metric conversion in every 1 meter, how many nanometers do we have? 10 to the 9. That goes in the bottom. Nanometers cancel. Meters is going to cancel. And then our second to the -1 is going to cancel our seconds over here. Guess what? We have one unit that we're left with, which is joules. All we need to do is to multiply out and divide the numerator divided by the denominator to calculate our E in this particular problem, which is the energy of just a photon. Okay, so we evaluate this. And again, this may seem simple enough, but often this poses a challenge for students, specifically how you enter it in your calculator. For example, can be problematic. Make use of the parentheses when you do this in your calculator. Okay, so if we do this, calculate this, what we find, let's jump down here. In part B, we see that our energy being equal to 3.8 times 10 to the negative 18 joules. Okay, 3.8 times 10 to the negative 18 joules. All right, if you think about the answer, right now, it makes sense based on the unit, right? Because we plugged everything into our equation. Joules was the only thing left. So that makes sense. That tells us that we've set it up correctly. And then the actual magnitude of the answer also makes sense because if we're looking at the energy of a single photon, this really, really tiny packet of light energy, it should be a really, really small number as well. Okay, so 10 to the negative 18. This makes sense for the energy of one photon. So in the next section, or the next part of the problem, we're asked to calculate the maximum kinetic energy of an electron ejected by the photon in the part B that we just calculated above from a metal with a binding energy of 3.7 electron volts. Now, we are given here the binding energy. Okay, so the binding energy, which if you recall is W in the equation we saw before. This is given as 3.7 EV. That's a new unit of energy we haven't seen before. That stands for electron volts. Okay, and there should be a conversion between EV and joules, either in your text or in your Alex data on the right side. That will show up, and that relationship is 1 EV equals 1.602 times 10 to negative 19 joules, right? That's not something you need to memorize. You can look it up, or you'll always be provided with it on a quiz or an exam if you need it. So we're given the binding energy of that particular electron, and then we need to calculate the maximum kinetic energy, right? So we need to find the kinetic energy of the ejected electron. Right, so we shine some light on this metal. That light, the energy of the photon of the light is 3.8 times 10 to the negative 19 joules. And we're told, or given the binding energy, we need to find once that electron is ejected, how much kinetic energy does it possess after it leaves the metal surface, right? What's the energy of motion associated with it? So we can use, right, our equation that we saw before, which was, we saw that energy, so H nu, okay, that's of the incident light that's being shined on the metal is equal to the sum of the kinetic energy of the ejected electron plus that work function, that binding energy. So if we want to find the kinetic energy, we can rearrange this equation just like we did previously. So kinetic energy here would be equal to that energy H nu minus W, the binding energy, right? We found H nu before, right? That's the energy of the photon, the incident light. So we can take that and we can substitute it down here. That's our H nu. And then our W is 3.7 electron volts. We can plug that in. Obviously now we need to change the units because the energy of the photon is in joules. We're given the binding energy in electron volts. So we need to convert that into the correct unit. So we substitute our values. We have our kinetic energy being equal to H nu, which we found before. So 3.8 times 10 to the negative 18, and then that's joules. And then we're going to subtract now the binding energy, which was, what was that, 3.7 electron volts. And we can set up that conversion here. So 3.7 electron volts over 1. 1 electron volt is 1.602 times 10 to the negative 19 joules. Okay, we set that up in our conversion. Electron volts go away. Okay, so left here on this right term is joules. And that makes sense because we're going to subtract joules from joules. And we can now evaluate that, and we end up with the kinetic energy being equal to 3.2 times 10 to the negative 18 joules. Okay, again, a very small value because we're looking at the kinetic energy of one single electron. Okay, so this is something you want to keep in mind for all of the calculations that you do. Okay, and this is a way to just to check to see whether your answer makes sense. Is the number that you get, is it in the right ballpark, right? Should it be a big number? Should it be a small number? And in this case, we're predicting a small number because it's just the energy of one single electron.